Okay, we have here our first question of this second part. Student sets up the electrical circuit below with 1, 2, 3 resistors in series with an ammeter and a 12-volt battery. We also have here an open switch, which is proving this little short circuit here to be not working at the moment. So let's have a look at this question here. The ammeter displays 0.1 amps. Calculate the potential difference across the 45 ohm resistor. Well, this was using Ohm's law, V equals I times R equation. The current flowing through is 0.1 from the ammeter reading. That's what ammeters measure. The resistance is 45, so 0.1 times 45 gives us 4.5 volts. Now the second question here, calculate the resistance of the resistor, R, is tricky. There's two ways of doing it. Both cases though, you've got to know there's a couple of circuit rules. Now in this case we have a series circuit with all the current able to pass through each of these resistors in turn. In a circuit rules, in series circuits, the potential difference that is put in is shared between the resistors. So it splits. The current is what's the same all the way through. So we could use that idea there, and similar to what we've just done over here, work out the potential differences for these two. Knowing what we put in, we can work out the difference. Let's do that very quickly. So in the same way that we had 4.5 there, by 0.1 times 45, we'll do 0.1 times 60 here, and that gives us 6 volts. Well, if we've got 4.5 and 6, that gives us a grand total of 10.5. If I put 12 volts in, the difference between the two leaves us with 1.5 volts. And then we put that back into the Ohm's law equation. 1.5 equals 0.1 times R. Rearranging the equation, we want to get rid of the 0.1 times R, so we take it down the bottom, 0.1 divide, cancels that out, which leaves us with R as 15 ohms. The other way of doing this is treating the resistors in series as one resistor, or the total resistance of the circuit. And we'll do that over this side. The total resistance of the circuit can be found because we know the total potential difference. We know the current flowing through all of them. Like I said before, it's 0.1 all the way through. So just substitute that into V equals I times R. So again, if we rearrange, take the 0.1 down to the bottom, that cancels with that. R for the total circuit is 120 ohms. However, we've already got 60 ohms there, 45 ohms there, so take both of them off this, and you're left with, lo and behold, 15 ohms. Okay, state what happens then to the total resistance of the circuit and the current through it when switch S is closed. Bear in mind that this is a 2-mark question. So we've got to put in 2 separate things for this. And just if you read carefully, what happens to the total resistance of the circuit and the current. So first of all, what happens to the total resistance? Well, if the current no longer has to just go through that resistor, it has the option of going through there where there's a very low resistance, then most of it will go through there and a tiny amount will go through here. So the total resistance of the circuit will have decreased. If the total resistance has decreased, well, if it's resisting less, the current, I, is going to increase. Okay, if you have a look on the other page on your paper, you'll see the experiment they're referring to. In this case, it was a copper block, which is a solid, and solids heat transfers through conduction. Determine how much energy was needed to increase the temperature of the copper block by 35 degrees. If you cut across So the line from 35 degrees and down, you'll see that it is 35,000 joules. We're now given a mass, and we have to find out, using our answer to part B, to calculate the value for the specific heat capacity. So this is actually on your equation sheet. So you write down the equation. Energy is mass times that specific heat capacity we're trying to find here. So that there is that bit there. Times the change in temperature. Well, we know the change in temperature, so that was 35, so let's substitute that in there. C is what we're trying to find out. The mass is 2, and the energy is 35,000. So substituting in, we've already got 1 mark. We then need to rearrange, but before that we simplify. So 2 times 35 would be 70. And so then we just rearrange and take the 70 down the bottom, and that will leave us with C on its own. So C ends up as 500, and we've got to give the units as well because they're not given here. So it's joules per kilogram degrees Celsius. These experiments, the specific heat capacity, don't ever really give the completely correct value for specific heat capacity, and because energy is lost out of the block. Often you'll find that some heat's lost out through the heater at the top, or through the gap between the heater and the metal block, or actually if you just actually touch the block, it's very hot anyway, so it's losing energy like that. So not all of the heat energy is going through to our little thermometer that sits at the side. Some is warming up the environment, so you're never actually going to measure the exact specific heat capacity. Okay, final question. Describe the methods that the student can use to calculate the densities of these two objects. It's a metal cube and a small statue. Without going into all of it, you need to know that the density is the mass divided by the volume. Now, the big problems I've seen off this, for even those people that actually understand the experiment, is being thorough enough to know and explain exactly which piece of equipment we should use. In both cases, you have to measure the mass. So you measure the mass. How do you measure the mass? Use a top pan balance, and you weigh it. You're not getting the weight, you're getting the mass. Okay, so that's going to be the same for both of them. Now we've got a regular object, and we've got an irregular object. In this case, because it's a metal cube, you could take the shortcut of times in one length by itself 3 times, or cubing it. But let's just be thorough. We calculate the volume of the regular block by doing the length times the width times the height. But let's be thorough. How do you do that? You do it by using a ruler. That then gives us the volume. We make it really clear in our question that we know what the equation for density is. So we say you take the mass from the top pan balance and divide it by the volume, and that gets you your density. And that's pretty much it for the regular object. Let's have a look now at the irregular object. Well, in this case, what you need to do is what we normally do is put it into something called a Eureka can. Now, I can understand actually why some people maybe didn't say that, or a displacement can, because the statue is quite big potentially. But the same principles apply. Fill up a container full of water up to the brim. We dunk our little statue in here, and overflows the water, but we need to catch it, and we catch it, and then we measure however much water has came out using measuring cylinder. Not a beaker or a bucket or a jug or anything else I've heard, using a measuring cylinder. So the water that comes out now will give us our volume. If you measure the mass of the statue, again, talk about the equation, mass divided by volume gets you your density.